So the network theorem is nearly almost similar to Thevenin's, but whatever changes is that the source now becomes the short circuit current. So how we need to state it and also know the formula and do some applications and examples. So we need to have it states that the current that flows in any branch of a network, any branch of a network, any branch of a network is the same as that which will flow, is the same as that which will flow, the same as that which will flow in the branch if it were connected, flow in the branch if it were connected across a source of electrical energy, if it was connected across a source of electrical energy, across a source of electrical energy, comma, the short circuit current the short circuit current being connected across the conductive branch, the short circuit current being connected across, it should be connected across the branch, comma, while replacing all the EMF sources with the internal resistance while the current sources with open circuits. So I of the load, or this is a formula, or not just before that, procedure. Let us identify the procedure you're going to be following. So procedure number one is you should circuit the branch. Short circuit the branch containing the load. Procedure number two is remove all the EMF sources and replace them by the internal resistances. Remove all the EMF sources and replace them by their internal resistance. Replacing it by the internal resistance. And Roman 3 is also determine the short circuit current. Number 4, determine the current flowing through the load. using the formula I supposed to be I of Norton's internal supposed to be Norton's internal resistance over Rn plus R of L multiplied by the short circuit current. So that's basically what it is. From here, we're going to have just an example of the circuit. So this is example 1. So we're going to have the example 1. This is example 1. This is 30 volts. The angle is 5 amps. We shall go through the resistor. And the direction of the current, let us indicate the direction of the current or of the supply as that one. Then we shall have this as AB. We shall have so this is 20 volts. The angle is 15. The angle is 15 volts. This is 5 ohms, and this is 10 ohms, and this is 20 ohms, which is RL. So the example 1 is using Norton's theorem. Determine the current flowing through the resistor, load resistor. Determine the current flowing through the load resistor, 20 ohms, through the load resistor. Ohms. So once you're given such a question, the first thing you need to do is for you to short circuit the load. You're going to short circuit the load, and anytime you short circuit the load, you're going to connect a short circuit path in this path. So this path becomes our I of SC. So that when we draw that in circuit, it's going to have. So the first thing is a short circuit the load branch. So the load branch, we shall have our circuit appearing this way. And this is the short circuiting path. So let us take note of the direction of current. So when you short circuit this load, so this becomes the short circuit current. Because the currents are going to arrive at the same point, and using the Kirchhoff's current law, the sum of currents arriving at the junction determine the direction. So when you look at that, we shall have a short circuit current I of SC being equals to V1 over R1 plus V2 over R over R2. Because these currents will arrive at a common junction and go through the short circuit conductor. We shall have I of SC being equals to 30 angle 15 degrees volts over R1 is 5 plus 20 angle 15 degrees volts over R2 is 10. When we divide this, we shall have this as 6 angle 15 degrees amps plus 2 angle 15 degrees arms. But all these are polar. You cannot add them. You need to change them into cartesian, into rectangular, because you cannot proceed with that way. That means you have to change that into rectangular for us to be able to get to add them. So you'll have 6. So this becomes 5.796 plus J 1.55 plus this is 1.932 plus 0.51 0.52. This is J 0.52. So we add the two so that we can get the short circuit current. 5.79 plus 1.5, 1.932. This becomes 7.728 plus J. .07 amps. Change this also, or put them into polar, because when we shall be multiplying, we shall multiply them in a polar. So we already let us prepare our answers in a polar. So this becomes 8. The angle is 14.99, 14.995 degrees amps. That is the short circuit current. So from there, we are going to determine the Norton's internal resistance. Norton's internal resistance. The EMF sources will be replaced by the resistances, by the internal resistance, and we shall have the EMF sources or the circuit being equivalent to this way. We shall have our circuits. So this one is 10 ohms. Let me just read. This is 10 ohms. This is 5 ohms. And we shall have our circuits appearing this way. By looking in, then we shall have them appearing. So we shall have R Norton's supposed to be 5 times 10 over 5 plus 10. This is becomes 50 over 15. 15 over 15 is 3.33 ohms. So we draw the Norton's equivalent circuit. Shall have R Norton's equivalent circuit. We shall have our source here being the I of SC. So this becomes the I of SC. And we shall have the resistance being this internal resistance connected in parallel with the load now. Our load was 20 ohms. 20 ohms. And this will determine the Norton's resistance 3.33. So this becomes a circuit. So the current through the load 20 ohms resistor is supposed to be Rn over Rn plus RL multiplied by the I of SC, short circuit current, which means supposed to be 3.33 over 3.33 plus 20 multiplied by the short circuit current in our case is 8. The angle is 14.995. So it looks like that is 23 is 3.33 over 23.33 times by 8 multiplied by 8. The angle is 14.995. When we have that, we shall have our answers 1.142. The angle is 14.995 amps. So that's our answer. So this is going to be our second example, and from the previous example, the only difference is that we have now inserted the capacitor, the inductor, and the resistor in series, and this time it's going to give us a bit of complex calculation. So the first thing we still will have is to short circuit the branch AB. To short circuit the branch AB, we shall have our short circuit current being equals to V1 over R1 plus V2 over R2. This is R2 and this is R1 in that case. We shall have that as 20 over 4 plus 10 over 2. This is 5 plus 5. This becomes 10 amps. This is I of SC. Then from there, we determine Norton's internal resistance. Determine Norton's internal resistance. So the circuits are going to be in parallel. We shall have our circuit appearing this way. So this is 4 ohms, and this is 2 ohms, and this appears to be in parallel. So R of N is supposed to be 4 times 2 over 4 plus 2. Because they are in parallel. That becomes product of sum. This becomes 8 over 6. Becomes 1 point. 8 over 6 becomes 1.5. 1.33 ohms. So from there, we draw the Norton's equivalent circuit. Norton's equivalent circuit. Our source becomes our short circuit current, which is I of SC. Then we shall have what I refer to as the Norton's internal resistance. We shall have our load being equals to the path through AB. J is 2.95. This is 1.37 ohms, and this is 1.33 ohms. Our short circuit current becomes 10 amps. Then we shall get the current through the load AB, current through the line AB is supposed to be R Norton's over R Norton's plus R of L multiplied by I of SC. And that one becomes 1.33 over 1.33 plus 1.37 plus 2J, J 2.95. All this is what we're going to multiply by 10. When we have that in place, then we're going to have 1.33 plus 1.37 becomes 2.7. It becomes 1.33 over 2.7 plus J 2.95 multiplied by 10. To change this into polar, so it becomes very easy. We shall have 1.333, the angle is 0, and that one into polar. This is 3.99. The angle here is 47.53. This is what we multiply by 10. This implies that we shall have our value being equals to our answer being 3.33. The angle is minus 47.53 amps. And that is it. So we have done the last example. We shall be able to proceed from there. So we shall be able to have other two examples that applies. And please check on past papers and see these applications are. You can be able to utilize them well. So that as we go over, as we prepare ourselves to be evaluated, we have the knowledge that requires for us to get to where we have to get in terms of professional growth. So that's what we shall be having. We have done today. So next lesson we shall be able to continue with Norton's with another two examples. Then we go to another theorem again. So until we meet again, then let us cooperate. Let us review our knowledge. Let us check on the past papers. Let us check on the application of the questions that we are doing. Then thank you.